Maybe a good idea is to have a small recap of what we did a couple of days ago. Forget about the mathematics, just what we did physically. Now, the evil part of me would say, well, we have to be people who should be able to explain in full detail what we have done, because... Okay, but we'll see what's going to happen. Let's see what's going to happen. Let me give you a small recap then of last Tuesday's lecture. What we did was the following. We started out with a proton and or a neutron. It doesn't matter which of the two, because we're going to ignore the Coulomb interaction between particles. So as far as the strong nuclear force is concerned, protons and neutrons are almost fully equal. So you have a proton or a neutron. We're going to assume that the interaction between them, the strong nuclear force, only acts in a certain distance, doesn't depend on direction. And we're going to add another proton or neutron. And it doesn't matter if we try to add it here or over there or over there or over there. So you have this sphere, and on this sphere you have everywhere exactly the same interaction between the two. In other words, what we have here is that the potential energy that these things feel because of each other is, as it's called, a central potential. Central is exactly that it doesn't depend on direction, only depends on magnitude. So that gives you a sphere. And we made a crude approximation of what the potential energy is going to be. Namely, we said, well, you know what? I'm going to model it as such. There you go. As a function of r. And then it goes to infinity. That was the idea. Right here you see the distance from one proton-neutron to the other proton-neutron, and the typical distance that you take is, well, the size of that the nuclear force breaks down, which is of the order of magnitude of 2 times this number here. There you go. So there it is. The only thing that we did, but it took us a few hours, was that we took the Schrödinger equation, put in this potential, and we solved it. And it's extremely important for whatever you're going to do later in either nuclear physics or anything that has quantum mechanics in it, that you know this little trick. The idea of splitting your Schrödinger equation into a radial part and an angular part. So I'm just going to write it down. Again, the details of mathematics are not that important. It's really just about how do you do these things in the first place. This is the Schrödinger equation in 3 dimensions. Plus I h bar ddt. There it is. And in case of a radial or central potential is what I meant. Radial potential is the same thing. Central potential. This equation beautifully splits up in 3 differential equations. A time-dependent part, which always has exactly the same solution, which we all know by heart. Or we should. Yes, that's the one. So that part is easy. Then we have a angular part, the part of the solution that only depends on the angles theta and phi. And again, this is a set only for central potential, this part. Then you will always get that the angular part is always that same thing, these so-called spherical harmonics. There you go. Somebody has solved this for you. I think it was Laguerre or something like that, some guy. And the spherical harmonics you can just easily look up in the table. By the way, it's a very worthwhile exercise to just derive the spherical harmonics for yourself just one day. It's something that you do only once in life, and that you solve them, you know at least that they exist and how they work and everything. Otherwise, it's just this big mystery that you have these functions that apparently look like this and such. They have very special properties because they come with L's and M's. They're introduced if you solve the differential equation for the angular part. That's the thing that I just advise you that you might want to do at some point. Then you see exactly where they come from. The mathematics tells you that the solutions only exist under the condition that these L's are integer numbers and that these M's are also integer numbers, and they're squeezed in between the plus L and the minus L. Why? Because of mathematics. There's really no physics behind this. It's just the mathematics tells you that this is the case. And as a result of this, that means that every spherical harmonic comes in 2L plus 1 varieties. Varieties. I think this is correct spelling. Somebody should really correct me if I'm wrong. This is
there's an E on the I.
Yeah. Really? Another one?
Yeah.
Thank you. Okay. That's the correct varieties. Alright. And this comes again, this is just mathematics, but it comes with a very important physical implication, and that was the word that was mentioned last time, namely degeneracy. And degeneracy means that you have multiple solutions to a Schrödinger equation that have the same energy value. That is what degeneracy is by definition. And you can already see it happening here. I'm going to take a moment for everybody to really appreciate what's going on here. What you see here is that the only thing that fixes the energy is either this part or the part, the radial part I'm going to write down in a second. This angular part, the spherical harmonic, has no energy dependence in it itself. It's completely independent of what the energy is. Yet, this thing comes in 2L plus 1 varieties. So that means that once you fix the energy, then these are still free to have 2L plus 1 versions of them. In other words, if you combine these three solutions together, you get this one thing that has one energy but 2L plus 1 different solutions. So there's always going to be 2L plus 1 different solutions with the same energy. And again, this is called degeneracy. And it directly comes from the spherical harmonics. You already knew this from maybe your atomic physics. You know that every orbit comes with a specific energy, but you can put multiple electrons in one orbit. The fact that you have one orbit, so you have one solution to this, the radial part, in a second, but they all have the same energy is because of this. The degeneracy tells you that this one orbit, this one radial solution, can have multiple particles in there, all with the same energy. This is why the first orbit has, you could put 2 electrons in. Why? Because that energy comes with L is 0. And then there's 2L plus 1, so that's 1, but they come spin up and spin down, but 2 particles. And the second orbit, the next energy, gives you L is 1. Do the math, you get 8 particles you put stuck in there. Anyway, and that's how you build it up. Same thing, nuclear physics. Alright, and then there's the radial part. Now the radial part, these two are the same for every central potential, so that's easy. Somebody solved it for you. Just have to solve the one. And the radial part is a differential equation, which unfortunately is a little bit difficult. But by using a nice little substitution that I showed you last time, let's see what it is, 2m h bar squared L plus 1 plus VR. This is the radial differential equation. The original one had a psi here. Maybe you remember from a couple of days ago, but if you do a little nice substitution, that differential equation becomes somewhat more simple and you just get something that resembles the original Schrödinger equation. And from this moment on, it's just try to calculate away. So this is general, this is for all central potentials. Again, it's all a big recap of last time. I'm going to apply this to our nuclear potential, our crude approximation. You'll remember this? We plugged in this potential into this equation and we solved it. And what came out were radial solutions. They came in 2 varieties. Bessel functions and Neumann functions. I think, I don't recall, it's either square root of r or 1 over square root of r, but it doesn't matter for the rest of the argument. I forget what it was, I have to look at
square root of r, I think.
1 over square root of r.
Okay. Okay, that's what, yeah, that's what I remember. Something like this, yes. It has a Bessel function, and the Bessel function comes with an order, and it comes with an argument. The argument in our case turned out to be 2me h bar minus v, square root of r. There we go. And the other one was the Neumann function, with again a complicated argument. Here should be squared, there's a square root. That was that. This is just a mathematical solution to this problem. So what did we do next? Because at some point we found matching numbers, the first couple of them. Somebody can take over? Because this really is the meat of this week's lectures. That you understand what happens next.
Well, then you apply the boundary.
Table.
Yes. 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 What we're going to do, we're going to apply the boundary conditions that fixes a couple of these A's and B's and such. And there was a boundary condition that fixed the energy. And it turned out that that one was discrete. It only came in certain values. The alpha here, by the way, was L plus 1 over 4. Again, mathematics. Okay, boundary conditions. One of them said, well, if you integrate all over space, so you're going to look where this nucleon is, if you put the other one in the middle, whereas the other one, you only get a probability distribution. But one thing that you know is that if you integrate over all space, you're bound to find the particle. It should be somewhere. In other words, this should be 1, integrated over all space. And it turned out that if you took the Neumann functions into account, that just the mathematics doesn't allow you to get the number 1 out. It doesn't even give you the number 8 or 5 million, it gives you infinity. Now infinity you cannot do anything with. So fortunately we have the freedom to choose our integration constants A and B in such a way that we can just, we can choose whatever we want. So just for physical reasons we're going to say, well, at the very least we want the integral of this thing over all space to exist. And if we want it to exist, as in not being infinite, then B has to be chosen as 0. So we got rid of this part. Second, if you do this integration, we didn't do it explicitly, but if you do the integration, a number will come out. Could be 5 million, could be 8, could be minus pi, but a number comes out. The number has to be 1. That's not an issue. Just choose a appropriately to whatever comes out, make sure that it's rescaled back to 1. This is how you pick a. So this one we can fix as well. Now for the energy. How did we get the energies out? That is maybe the key message, because this gets us to the magic numbers in a second.
We found the zeros.
Yes,
the inner function.
You're right.
You
Right.
define that the psi r is 0 for r is equal to
Yes.
or bigger than r0.
Yes, thank you. We have one important boundary condition to go still. One boundary condition that we used to fix B was the integral should not be infinite. One boundary condition that we used was if you integrate over all space, then this should be 1. We have another boundary condition, and that is that the particle is not allowed to be here at value r0, or outside of that. So here's a boundary condition. This thing should be 0. There should be no chance of finding the particle on the edge or outside. So it should really be like this, that one. Now we've exhausted our integration constants. We've already fixed A and we've fixed B. So the only thing that we can use still to fix this boundary condition is by fiddling with the energies. Now how do we get this thing to be 0 at this position? Well, the only way that this can be 0 if A is not 0 is to make sure that this thing is 0 by itself. And the Bessel function, maybe you took the time or a moment to look it up, it's sort of like a sign that will become smaller in space. It is 0 at certain points. 0 right over here, 0 right over there, it's over there, there. Many places it is 0. So, what we want is this Bessel function with this complicated expression to be 0. And if we do that, then this is fixed and we're done. And that's how we did it. So we took this argument of the Bessel function, which mathematics told us was this, h bar squared times r. We take an r0 on the boundary here, and we force this argument to be that number that makes the Bessel function 0. And I call these numbers J0, something like that. This is my own personal notation. Now if you then, and these you look up in the table, and the next step then is, well, you know that the square root of E has something to do with this 0 of the Bessel function, so E is proportional to the square of the 0. So E ultimately will be proportional to the squares of the zeros of the Bessel function. That's what we did. Lots of mathematics, but here's our physical end result. Because the next thing that we did is that we looked up the values for the zeros. We found the energies, they're discrete, right? Energies can only have very certain values. For every zero there's a number of values for E, and no values in between. So that allowed us to make a graph of all allowed energies. And when you did that, including the degeneracy that we saw here, you found that there were groups of energies that are very closely packed. And there will be a gap, and then there's another group of energies that was closely packed. And we know because of the degeneracy exactly how many particles we can stick in each of these levels. And they just counted how many you could put in there around this energy value. And you found, oh, the first one allowed 2. The second one allowed 8. Those were matching numbers. That's how we did it. Because apparently if you stick 2 protons together, the first energy level was somewhere over here, and it was only 1, and you could put 2 in because of spin. Apparently if you stick 2 of them together, that goes very easily. It takes only a small amount of energy. But if you want to stick a third one in, all of a sudden you have to make this huge jump. So sticking a third one in all of a sudden requires a lot more energy. It's a huge step in energy. So apparently 2 is more stable than putting 3 together. But once you have made the step of putting 3 together, we found that you could stick 8 in here as well. 8 of these things. So apparently, if you're going to make the jump anyway, then you might as well put 8 together. And that is more energetically favorable than 9. And that's how we got the matching numbers. And lo and behold, they agree completely with, if you do the experiments. These are the first 3. What was it, 2, 8 and 20 or so, something like that.
Yeah. 2, 8 and 20.
Okay. And after that it broke down. Why did it break down? Because these 2 things don't like each other very much if they're protons. They try to repel. That's the Coulomb interaction. Want to give it a go? The floor and the board is all yours.
Well, we mentioned A,
Yeah.
and then the problem started.
Okay, well I know. It's a, no. Let me give some general idea of this exercise. It's certainly not to find the solutions, because I know that it's very complicated.
We read multiple articles saying that if you use the VR function, that you cannot even do it analytically.
Okay, so that means you have to do it numerically, or by some approximation scheme.
Yes. Which were very hard to understand.
Okay, now in all seriousness, this is really why I give these exercises. I know full well that they cannot be solved fully. I know.
So great! Okay,
no, it's not me. No. This is research-based as education. At the moment that you become a scientist in whatever field of natural science, you constantly encounter things you cannot solve. So the question is, how do you go on solving them?
I considered printing out the article for everyone so they could read it.
What article was that?
Well, we found Woods-Saxon's article, an article by Meyer herself, who basically use experimental data to do it numerically, but that was a lot of work.
I know.
So,
So here's my assignment. Could you, as if you were giving a lecture, just build up what the problem is, what the first steps are, and how you attempted to solve it, and where the problem lies.
sure.
And again, it's not about finding the answer, it's about seeing how well you've done research. So the floor is all yours. Can I ask the audience to pay exactly close attention to those criteria? How well do you understand what they're telling you? So please don't talk to me because I sort of already know what you're going to say. As in, I know the nuclear physics. Could you talk to the other people and try to make it as understandable as possible? Again, that's not a measure of how well you solve the exercise. How well can you communicate what you've done and where the problems are? So everybody, please pay attention to exactly those criteria and see what happens.
Let's see. So, well, I mean, I'm just going to work this out. We started with like the center potential modeled after a infinite well, which is this, but that's obviously not very realistic because that basically only models the part where the forces between a neutron and a proton or a proton or whatever suddenly just disappear and become infinite to like overcome. And
So we graphed out the potential.
yeah, so in our problem we get given a center potential VR. That should be a more realistic representation of the what happens here, right? At the boundary of the strong nuclear interaction. Which, first of all, we just graph this with some simple numbers and to just see what it would look like. What? That's what we did. So the graph basically looks like this, where your V0 is down there, is where it starts. And instead of making a right angle, it makes this slope. And then it tapers to 0. Well, wait, that's not a...
It's just kind of like levels out.
It levels out.
Like,
It basically is a limit, which is at 0. The limit is at 0.
so,
And on the axis you have R.
so yes, the question asks us to kind of try and figure out what each of what sort of V0 was, what the large or capital R was, and what A was. And so from kind of playing around with numbers and like just trying to see how they change the graph, I guess.
No.
Yeah.
Online lecture.
Oh yeah.
There's a really good Indian lecture online on YouTube
Oh,
that explains it very nicely.
It's very good intro music. So from kind of playing around with the graph and seeing how it changed or how it shifted, we figured out that the capital R is just the inflection point. It's the point where it like starts to curve up.
So here it goes like that, and there it goes like that, and this point is an R, right?
I think it was it that one? I don't remember. It was one of the points where it like started to curve.
Oh, it's the inflection point.
Okay, then in which case you're right. And then from our helpful Indian lecture, we found that so A is, hold on, wait, you have that written down.
I have it written down. I have it written down.
Hmm?
I have it written
Well,
down.
thank you for saving me there.
Also, we found an expression for
Oh yeah, there it is.
R equals an R0, which can be found experimentally, and A 1/3, but
That's interesting.
I'm not sure where the A 1/3 comes from.
I will come with questions in a second. And yeah, just continue your presentation.
I think it's probably dependent on what kind of like nucleus you're looking at, but that's not so important for us.
Yes, we found that then the smaller a is the charge distribution. And yeah, YouTube videos. Which would then
the small a is also usually this distance. Basically, the distance from where it starts going up to where it reaches a limit. So that was first
that was
part.
that was
Okay.
the easy.
That was the easy part.
Okay, I'm going to interrupt for a second. Are there any questions so far? Because I have some, but maybe you do too.
Go ahead.
Maybe the physics, maybe the mathematics. On? So crystal clear to everybody, apparently?
So you found the R and the A, like the big R and the A from the graph, from my graph.
So we started off by kind of playing around with the graph. So we found that for messing around with it, that I mean,
Well,
that
just
like
graphing it in there.
yeah. Hey, that's but yeah. So we found that like when you change the smaller a, it would like stretch out the graph a bit more.
Yeah.
And then for playing around R, it changed like the flat part. I think it like changed the amount of distance there was between starting to curve. Yeah.
Can you like justify this physically? Like why would those things be responsible for the shape in the graph?
Well, the A makes sense because if you have a largest charge distribution, then more charge, then you have more Coulomb potential trying to keep it all together, pushing it all away.
Yeah. I mean, A divides the part that is the e to the x that changes now. The first part is just shifted over by 1 or v.
Yeah.
0, and I think A is always just the reflection point, which is e to change. Like, I think
The
E,
R is always the inflection point.
yeah, no, sorry, I mean A is the length of the whole thing.
Yeah.
Because like x divided by 2 or r divided by 2 without the minus r. And minus r don't.
Anyone else? Question?
Yeah, charge distribution in electrodynamics really is a thing. It's a measurable quantity. And what I want to know is a measure of the charge distribution, or is it the actual charge distribution?
That's a good question. Yeah.
Because the charge distribution would be how many coulombs per cubic meter or so, right? It's the number. And if I were to look up from some nuclear material what the actual coulombs per cubic meter would be in that material, would that be that exact same number, the charge distribution? Would it be your number A?
I think it's a measured one,
Okay.
but we're not sure.
Right.
But if you,
So it's a constant then.
yeah, depending on what nucleus you're looking at.
It's different for different nuclei?
Yeah, that was how it was presented
Okay.
in the tutorial.
So does that make sense to people, that the number A is different for different types of isotopes? Physics questions, not mathematics. I see people sort of hesitatingly nodding along. That sort of makes sense. Why? The answer is yes, but why?
Well, I mean, if you have a different nuclei, they have different amount of protons and
Yeah.
Exactly. That's all there is to it. If you put more protons in the damn thing,
yeah, then it's,
the charge distribution becomes much more dense. Yes. So would that make A a bigger or smaller number? put more protons in there, some heavy nucleus.
Well, it becomes more dense, so it should be bigger.
Okay, and does it make sense? Okay, so we understand just from physical hand-waving argument that it has to become a bigger number if you put more protons in there. Does it agree with its position from a mathematical point of view that A is exactly there in the formula? Maybe I should rephrase the question. The A.
Or the units don't match up then. Because if A is in coulombs, whatever you have in the exponential.
No, it's always coulombs per square per cubic meter, or a measure of that thing.
So then it would be e to the coulombs.
That would be wrong. I
Or
agree
e to
with
the
you.
coulomb inverse.
I agree, because these are just distances, yes? So these are meters, so the only thing that A is allowed to have as its unit is meter itself. So it cannot be the full actual coulomb per cubic meter. The units do not line up. So apparently, just by looking at the units, A is not the charge distribution proper, it's a measure of. Okay, and now back to my original question. If you put more protons in there, yes, this has to become a bigger number. Now, this becomes, the exponent becomes a smaller number if A is a big number. So what does it say about the shape of your potential then?
Will grow slower,
It will grow slower.
because this one is smaller, right?
Yeah.
Reading that correctly.
But just as an example, let's pretend the whole part of E goes to 0, no? Which would mean A goes to infinity, I think. That would make it to the original problem where VR is just V0, you know? So maybe tackle it that way.
Oh, I see.
They pretend the E part goes to 0.
Yeah.
When does that go to 0?
Like,
Yeah.
It's good line of reasoning, yes. If you put an enormous amount of protons in, yes, then an enormous amount of protons. So in our understanding of what A is as a charge distribution, you would expect A to become a very big number. But if A becomes a very, very big number, then the exponent becomes a very small number. In other words, at some points this becomes negligible, doesn't it? Or goes to some finite value or so. But that means this thing becomes a constant.
Yeah.
Constant-ish?
It's just like the before the punch guy.
Yes.
Just a straight line on R0.
Yes.
So then means when A increases by an
Big amount.
enormous amount, yeah, it will reduce to 0. Which means the
No, it will not reduce to
uh,
zero. It will reduce to
reduce
constant
to
value.
constant, yeah.
It will
Yeah.
reduce to constant value, regardless of the value of R.
Yeah.
Okay, so there would be no cutoff.
Yeah.
It would just go on forever, or very slowly. Very slowly go to zero. And I guess that makes sense, because if you put more protons in, let me put it this way. The more slopey it is that a word?
yeah.
Okay.
Just
I mean,
okay.
it is now.
Okay.
The lower the slope.
Okay, the lower the slope, the more chances there are of finding your next nucleon outside of this radius, outside of the box of R. Does it make sense?
Yeah,
Please,
Yeah.
fill out the details. Because you're right, it does make sense. Why?
Well, I was saying, like, if so if you have more nucleons and you have more of like places where you can put them, right? So thinking of like the
Yeah.
energy level in the inside the nucleus, you can fit, like, you have to fit more in there, so there's more of like going further away from the potential of that. Did that logic work?
I'm not sure.
Because I was thinking about it, if like you have like the energy levels is like fixed sort of thing, and then you have like a point where it's just you can't fit anything extra in there.
Yeah.
If that makes, or have I misunderstood that?
I think you're right, but I think I'm going to say the same thing without making reference to the energy levels.
Okay.
But I think you and I are in agreement. It's just that you use different vocabulary to get to the same point. If we have a big charge distribution, so you put a lot of protons into it, this becomes a big number, then your graph becomes much more like this, right? A is the size of its slopiness. In fact, you can actually see that if you take the derivative of this thing with respect to r, you get something. Write it down right now. So it will be minus v1 plus r minus r a squared becomes plus r over a, and then e to the power r minus r. Okay, that's the derivative. Okay. Do you see that at the moment, this is how much it's, this is the size of its slopiness. Do you see that at the moment, there's a plus here now, so it curves upwards. Do you see that if you put enormous amounts of protons in there, then the slopiness becomes very small. So it takes a while before the thing actually gets there. So you don't have to play around with some graphic calculator or something. You can actually just do the derivative and see it immediately. You see something else too, that the slopiness becomes small, right? But it does increase because of r. So it is small, but it will curve upward. It will go. Its acceleration will become a little bit bigger. It's because of this part. Except, of course, it makes r so big that the denominator becomes to come into play as well, and it reduces it again. So this is exactly why it starts out very flat, then tries to curve it upward, gets an acceleration, then all of a sudden curves down again. So you can already see everything just from the expression. Here's the thing: big amount of a means small amount of slope. Quantum mechanics tells you that you have now an enormous amount of space where you can expect to find a particle. Before it was only here-ish, around this area. Now it's this area and a little bit outside too. In other words, there's much bigger chances now of protons and nucleons not staying in the potential, leaking out. Becomes unstable.
And then it falls back, and then the A becomes smaller because you lose.
That is interesting. How that goes dynamically, yes. You're right, that's one step further along the line, but here you can already see. There is now...
But then the big R is dependent on the A then?
It is,
Yeah.
yes. Because big R, as you wrote down before, big R itself depends on the number of on big A, capital A. So yeah, it's very interesting dynamical problem how to solve that. But just to stay here, first of all, what you see here, big A means you get a big nucleus. The nucleus takes more space.
Yep.
That's one thing.
For people who want to see here.
There's more markers over there. There's a fresh. Yeah. There's one behind you.
I don't think he's interested.
That is the blue one. But how's the big A different from the small A then?
It's big.
Caps lock.
This is the number of protons and neutrons put together. Okay, so anyway, back to my argument. Can you stay for a second? So, back to my argument. First of all, the fact that you have a large charge distribution tells you that the nucleus itself will increase. There will be more radius where the nucleus is, where you can find your nucleons. But if you recall from your quantum mechanics course, you can also go through a potential barrier. It's called the tunnel effect.
Yeah.
This is what gives you radioactivity, by the way. That there's protons that are now allowed to leak out of here. Not classically, that's impossible. You have to have a certain amount of energy to get through this part. Quantum mechanics is possible. You might remember this from your quantum mechanics course. So over here in the original one, this one in the blue, that was near impossible. The slope was too high. It's very difficult to leak particles out. Here the slope is much more slopey.
Yep.
So it's much easier for the tunnel effect to take place, for particles to come out. So that tells you two things. A big charge distribution will tell you that first of all your nucleus becomes bigger, and secondly it becomes unstable. It's much more easy for nucleons to fall out. Yeah. In what packets do they typically want to fall out?
Alpha particles.
Alpha particles, because alpha particles have this tendency to stick together because of their double magic. So what you get out here would typically be an alpha particle. You make this this A, small a big number. There's a high probability of getting alpha particles out. That's what you get. So yeah, it sort of lines up with what I would think of the charge distribution, or measured charge distribution, because what is exactly the reason for the strong force not to hold anymore? There's two. Can you fill the details?
Well, either the opposing force, your Coulomb propulsion, overcomes it.
Yes, that's
by
right.
having a very large charge distribution.
Exactly. So that lines up. It's certainly talk for a second, but I want to make that point. Large charge distribution means the protons are really pushing each other away against the strong nuclear force that tries to push them together. So yes, of course you expect particles to fall out. That's one. There's a second.
One nucleus becomes too big. And
Yeah.
They're too far from each other.
Yeah.
Exactly. The nucleus becomes too big, takes up too much space,
Yeah.
and if it takes too much space, the Armstrong boxer doesn't reach anymore, doesn't grab us as easily anymore. So you have two reasons now why big nuclei become unstable. The charge distribution pushes things out, and the strong nuclear force ends its range of applicability. Okay, very good point. Now this is interesting.
Yeah.
So that was that. Now for to solve this one. Let's see how you did.
Now comes back.
Okay. Now you haven't solved it, but again, this is completely expected. Because I'm
I'll just
because
write down.
because of people like that, but
I'll just write down what you get if you fill it into the formula that we have.
yes,
Like
please,
we start
exactly.
with.
And tell
And
me.
then I'll show you why you cannot just solve
Yes,
it.
and do it from a mathematical point of view, please, and from a physical point of view. These two things go hand in hand. No, we just did it. We started out with something mathematical, we turned it into physics. We can do the same thing with what you're going to write out now.
Let's see, we have this thing. Let me see, where is that? And at some point we were like somehow halfway through what we were doing yesterday. We come upon this formula.
And I don't know if you.
And then maybe we just erase everything.
This is all
The black part, the Bessel functions.
of it can go.
Oh, everything.
Yes.
Okay.
I can imagine you need some space.
Maybe.
Changed. Right, we come on this formula. And yesterday for us, our central potential was simple, it was just the V0. But this time you're going to fill in this one. That makes it a lot more fun. So.
Strange definition of fun, then.
Let's see, that's going to be n minus q over 1 plus g to the. Right? Just gonna erase this part. And the fun hint that we were given on Tuesday is that you can also write this one as an approximation by a Taylor series.
Do you want to go? All right.
I got it.
Over
Sorry, just a small question. But now it's positive order, no? Because at home I started to redo it, and the constant R is the negative R, and whereas this Taylor expansion is the expansion of e to the minus R.
Yes. That's true.
yeah, that's going to change it here a little bit.
Exactly. When I wrote it down a couple of days ago as a hint,
Yeah.
I had e to the power minus r. So it gives you an alternating Taylor series, whereas now it's just fully plus signs. Just pluses.
Well, I just replaced this with x to make it a bit simpler to write down.
Yeah, but still, there should be pluses.
It's also the denominator, so if you conjugate it, if you multiply it by e to the minus r, both the numerator and the denominator, the one in the
Yeah, but you
denominator.
can just sub it into the denominator right away.
Sorry?
You can just sub it into the denominator right away instead of doing any like algebraic manipulation to put it upwards.
But then you'll have like inverse. You could do it either way. I was guessing that's maybe what you're trying to do.
No,
So
just continue.
this is the right data series, right? Or
It is not, no.
So,
but that's what you.
I know, but
that you
well, they know I know. I'm being lazy and for good reason too, but because I wrote it like this.
Yeah.
yeah,
okay.
okay, yeah.
But the only difference is that it actually
there are
that
pluses everywhere.
that's
Yeah,
all.
that's
So,
you brought that up as well, I think, when we're doing the maths.
Well, I use up the series.
I'm not saying that now all of a sudden your calculation becomes much more easy.
That's why I did
That's all along, yeah.
The answer is 2.
It ends up being exactly the same anyway. You're gonna put that in there. So let's see, let's write it down. It's gonna be fun.
By some strange definition of fun, of course, yeah.
So I will also bring the e to the other side. And also doing everything times r squared to get rid of this one. But that's just what we were doing. Right? Think times r squared minus h bar.
I'm missing an image. Oh, there it is. Okay, yeah.
Right.
Yeah, it's over there.
No.
And this is where the problem starts. Because with our simple one, well, I mean simple in air quotations, you could just like substitute an r for something else and get rid of all of the annoying constant stuff and make it into a function that looks like the Bessel-Neumann relation. But if you do that for this, that's impossible because this one won't cancel out nicely. Or
Well,
is that-
if you use the exact same trick, that I agree. Maybe there's some other trick.
That's
I
what
mean, the trick that I used a couple of days ago, I devised explicitly for that particular differential equation.
Okay.
It's not some general trick that always works. So, if it happened to work for this particular example as well, it would have been a huge coincidence. But
I think I also had a question about the way you did it in the white triple, because
Okay.
at least the way that
we-
I started doing the maths on it is I started by like following the steps you did in the white triple to try and like figure out roughly what I was doing. But then you made some jumps into like the you sort of said, oh well, and we'll ignore the like algebra to this and just jump to the result. But I started trying to work through the algebra and I didn't fully understand. Because when you use your, you do a trick where the trick where you make the r equal to the square root of h bar
Yes.
squared, that one. I don't see how it cancels out this part because you have it. It's not like I understand how when you multiply by the r squared it gets squared and all that, but you still have the like 1 over e minus v0 term that doesn't get removed, but it would remove the e minus v0 part here, right? Or have I not?
I can tell you for a fact that the calculation works.
Alright, okay!
It's an unsatisfying answer. We would have to go through the algebra to show you in steps how it works. Trust me, it does. Of course, unsatisfying answer. Would love to go through it with you at some point. But as for now, I would like to see.
Yeah. So that's the first problem I had, because I could kind of figure out sort of by writing out like that you could get you could sort of remove the e minus v0, but it would still leave this section in. And then from trying, so my logic was just, well, assuming I know how to get rid of this, we'll just move on. And then, God, what did I do after that? That's a very good question. Then the next, again, so it wasn't so much problems in working out, it's just problems in understanding how you went through the steps that then meant that then we went on and we tried to look up different sites that were going through the problems. They all did the exact same thing that you did, and so it's like, well, skipping a little bit the algebra going through it. It's just like, that's not what I want.
Yeah. Which I was a professor once and did exactly the same. So one exercise to show that this is that, and it took me 5 days. Yeah.
But how would you get rid of
it? Yeah, that's the worst.
But how would you get rid of it? Because I understand that you would use some sort of substitution to make it clean it up a bit, right?
Yes.
And that would look somewhat equal to this.
So yes. This is a similar substitution that I made, or maybe it's the exact substitution.
This is what you used before. Okay. But if you then do the use v0, then you are stuck with this. But if you add if you do the whole VR thing,
then you just have the exact same thing.
The exact same answer as you had before.
In that case, we're stuck with a question.
Did you try to truncate your series at say x squared, the second polynomial?
Yeah.
Did you truncate your Taylor series at some point? Because if you leave it in that form, then it's irreducible, which is why you do the Taylor approximation in the first place. So maybe if you took off, I don't know, the third term, and so that should be a 1 over x plus half x squared, I think.
Yeah.
But in any case, if you truncate your Taylor series, then it should be reducible. Maybe I don't know.
So okay, maybe okay. This is how far you got into a few years.
Yeah, that's how we.
That's how far we got, and then sort of I tried going on afterwards, just kind of assuming that I knew what I was doing, and then I also ran into other problems.
Okay, but that means that we have a nice question that we can all work on for a second.
Mm-hmm.
So, because I have some suggestions. Yeah,
you could basically break off the Taylor series.
Well, that is the idea. Let's clean up a little bit, take this differential equation, put it over there, have an empty board and see how far we get, okay?
Yeah.
Correct.
Alright, so thank you guys.
Scrap paper then.
Let's see.
So you looked up a Woods-Saxon paper? You looked up the paper by Woods-Saxon?
Yeah, I did.
What did it say?
They started using not the Bessel functions. They started using something NU. I'll look up what it actually is.
Okay.
It sounded Russian.
NU.
No, it was in German. I had the Johnny from London. I think it was Hungarian. Mathematician. Anyway.
Sounds Germanic.
Yeah, it does.
Yeah, no, ours instead of x's, no?
Yeah, I'll do it in a second. Okay, for one thing that I'm going to do is I am going to truncate.
Then it's not accurate anymore.
No, but it was.
It will never be.
It was never accurate.
No issue there.
Okay.
No, really, because you already made this step before. I mean, from going from here to there, we already did that. At some point, we did something like this. Did that? That already is an approximation. Of course, the key thing here is to keep track of how many approximations you made and how valid they are. But that's a separate question. Because you can't just approximate anything by anything. have to have justification. Anyway, there we go. I think this is the differential equation that we have. I'm going to erase the rest. What I've done, I've truncated. I said, you know what, of this whole Taylor series, let's just take only the first two terms. Get this. And x, if memory serves, was r minus r over a.
Yep.
Okay.
What they used was the Nikiforov Uvarov.
Well, it's well known to everybody in the audience, I'm sure.
What?
Nikiforov Ur.
Call Eric. Eric can't do it too much.
Oh, okay.
It does sound Russian though. Okay, I have a tendency in these matters. There should be a square here.
Yeah.
Okay, I have a tendency. Should there be an r squared there as well?
Where?
Yes.
Yeah, they multiplied everything by r squared.
The r squared on the right term within the brackets should not be there.
This one.
Yeah, that's why we have. No, we have that one there
Okay.
because we got rid of the one on the right term of that bracket.
So they're divided by
so-
r squared,
No, they multiply r
Yeah,
squared
they
everything.
multiplied by r squared.
multiplied by.
So
Multiply
there should be an r squared.
here. There should be an r squared here. Oh wait.
Sorry. I think I'm only confusing it. This whole thing.
R squared. I agree. Yes.
Yeah.
Now it looks familiar again. Okay. Yeah, crappy situation. I'm going to write down the differential equation in form that is from a mathematical point of view. I'm just going to put all the constants, going to rename them. Just for notational clarity, that you know what it says there. If you look at this, and this part, everything has to be multiplied by u and then equal to 0. This is just a constant again. So that's just some number b. And this part consists of a constant times x times r squared, but this x itself is r-ish. So this part and that part becomes r to the third power. With some constant in front. This one and that one will become r to the power 4. Now, of course, if you multiply this out, you will get some additional constant that you can just, absorb in this one right here. Now, what the constants exactly are is important if you want to get all the way to the conclusion. But just from a mathematical point of view, this is your differential equation. This is what you need to solve. This is not easy. This you have to do numerically, unless you can find some clever trick.
We can divide everything by r squared.
You should also do it.
Yeah, but then we just reversing the step that they did before.
There should be a minus sign between the e and the bracket of e minus 2.
Which one is that? This one?
No, go to the bracket to the left. Between
After the e.
After the e, a minus sign. Yeah.
No.
What?
No, this is true. Yes, no, he's right. Yes, this is true. Okay, there we go.
But isn't it just easier to just leave it as e minus then v0, like without the bracket and the plus?
Well, this
Because otherwise you have just a section of brackets that aren't doing anything.
no, but now what we have is e times r squared.
Oh, but wait, hold on, what? Is it? Alright.
No, this is your formula, so I need to know if this is correct.
This is the correct formula.
Okay, in that case, we have e times r squared somewhere as well. I'm assuming now that I need another constant. It's called f instead of e for obvious reasons. Then it becomes something like this.
Yeah.
Watch me easy, yes? Are you sure about this though? Because when I did the calculation, I never ended up with r squared.
Well, I'll what I did. You can bring the r squared back under the like h bar squared L times L plus 1 over 2m. That's where we got the whole r squared away from.
No, this is correct. No, it's fine.
Yeah, so basically what we had before, we had our r squared here and not there and not there.
Yeah, okay.
And we just did everything with r squared.
I see. Alright, so any ideas how to solve this? There's a trick that we're going to use next week as well. It's called perturbation theory. So,
Oh, that's the thing we okay, yeah.
alright. The trick, I mean, if you want to do it full quantum mechanically, it becomes very difficult. And of course, it's something we have to study next week. But the idea is very simple. The idea is this. It's a linear differential equation. Despite how difficult it looks, it's a linear differential equation. The thing that you are solving for, u, only is in the formula to its first power, no squares or anything else, as its derivatives. The derivative of the thing you're looking for here, it's a second derivative, but the second derivative is to the first power. This is called the linear differential equation. And the linear differential equation has this very nice property, very easily prove for yourself, that if you have two solutions, then the sum of these is also a solution.
Yeah.
And there's a nice property that we discussed many times before. There's only going to be two solutions, not anymore. Okay, now why is this nice? Because we can do the following trick now. We can say, you know what? Suppose now that the solution that we're looking for is some easy solution, relatively easy. It's called u0 plus, well, it's called epsilon plus a small perturbation. So it's sort of this solution plus a little bit extra. That's the idea. And then typically what people do, this epsilon doesn't really mean anything, it's just the size of smallness. So it's only a small contribution. It's a measure of how small it is. Measure of smallness. Okay? Now, that will mean that the energies will also consist of the energy that corresponds to the easy solution, it's called E0, plus a small contribution. Epsilon this. Does it make sense to you that if you have a easy solution, it comes with this energy, but if you would add a little bit extra solution, it will also change the energy by some other number? That's this one. There's something else that's going on as well. That is that if you look at this thing, this also consists of an easy part, a big part, I think that makes a big contribution, and small corrections to it. Now, what would be the big part and what would be the small part?
The lowest r value, like the r squared, will be the big part, and this r.
Wouldn't it be the other way around?
Yeah.
That's fair.
No, because r is less than 1.
Yes. Is it less than 1? Why is it less than 1?
Depending on your choice of units.
Okay, in perturbation theory, what you try to do is find dimensionless units. You don't have that issue. Otherwise, all of a sudden, where you can truncate your series, you can depend on your units. You cannot. But it's easier to see in this differential equation that we have here, because if you look at our potential, look something like this. We already saw that over here-ish is where big R is. Here's R. So around this area, here-ish, R minus R is close to 0, yes?
Mm-hmm.
In other words, X is very close to 0 around that part, because 0 divided by A is still going to be a small number. Now if you have 0-ish, so X is 0-ish here. Do you agree with me that x squared is even more 0-ish? Because everything between 0 and 1 squared is going to be a smaller number. And to the third power is going to be even a smaller number still. So what we have here, under this condition, if we restrict ourselves to this area, we will have that x is a bigger number than x squared, and that is a bigger number than x to the power 3, etc., etc. Going back to this differential equation, that means that this part is x independent, it's going to be a big part. Well, it depends on your value of L. If L happens to be 0, then it's going to be 0. But this is going to be big-ish. This is going to be big. It's going to be bigger than that. So this part and that part is going to be your leading part. Your thing that will give you this part of the solution. And all the rest, the x squared, will give you a perturbation. So let me write down how I do this. Going back to this differential equation, I think that's easier. Yeah, we'll do that. dr squared plus e r squared minus, well, there's a whole bunch of constants there, but you know, I'm going to forget about this altogether because x squared is going to be small. You can easily add it in later yourself. Something like this, yes? Minus, I might be messing up some minus signs, but and that is of course important if you actually want to get to the answer. But if you're just interested in how you're going to solve this, and it sort of looks like this. Sort of like this.
Where did the r squared for the first term go?
I should have put it here. Correct?
And also for the h bar squared.
You are right. I stand corrected again. There we go. Alright, so it's this thing. Again, this part and that part are going to be bigger than this one, because this one goes with x to the power 3 or so. And this one will go with, well, no x whatsoever, and this one will go with r squared x. And you can revert it back to x squared. And write down what it then typically would look like. Plus e minus h plus 1 to m. Now you might think that I haven't done anything at this point. I've just grouped this one and that one together into this one bracket. But here's the thing that I'm going to do. This one again is going to be much smaller than this part. I've really separated the bigger parts from the smaller parts. So just to keep track of things, I'm going to write this epsilon here again. Trust me, the only thing that the epsilon does there is be a reminder to you that this is going to be smaller.
Yeah.
Alright, here's where perturbation theory starts. Let's write down now that our solution is going to be our general solution is going to be this thing here. Just substitute that. Plus E0 plus epsilon E1. So this one now has this contribution. R squared minus h bar squared plus 1 to m minus epsilon v x r squared u plus u1. Still haven't done anything. The only thing I've done, I've replaced my energies, general energies, by the main energy plus a little contribution. Same thing with the solution here, so I get this thing. Up to this point it's all exact. But if you would multiply this out, because there's all these brackets, you will end up with terms that are of size epsilon squared. And epsilon squared, because epsilon is small, epsilon squared is going to be a smaller contribution. In fact, what I could do is write this out. First write down all the parts that have no epsilons in there. Write down the parts that have only epsilons in there, and I can write down the parts that have epsilon squares in there. I will get 3 differential equations that I can solve separately. One of them will give my big contribution, this one. That one's going to be easy. It's going to be an easy solution. Then the First, the second differential equation, the one that gives you all the contributions that go with epsilon, will give you how much the distribution has been shifted, has been perturbed. This is all very abstract. Let me just write it down. That's much easier. If you multiply this out, this one here, let's write down everything that goes to the power epsilon 0. Help me out. What are these? Hang on.
E0. E0.
What must be a differential equation? Is the question clear to everybody what I'm doing here?
Yeah.
What I want to do is write out this whole thing with all the multiplications. You get this whole big thing that has parts that have no epsilons in there, you have parts that have epsilons in there, you have parts that have epsilon squared in there. I'm only looking for the epsilon parts now. Which parts are those?
Yeah.
The first term.
The first term, yes. Because this one, if I look only at the parts that have no epsilon in there, is this one, yes? Okay, and this one. Select only the parts that have no epsilons in there.
E0 r squared.
U0.
Thank you. What else is there?
The h squared and l plus 1 and l plus
2n. This one has an epsilon, and we're not looking at those. Times what?
u0.
U0. Okay, so apparently, if we restrict ourselves to the biggest contribution, that biggest contribution will obey this differential equation. Does it look familiar? That's exactly the Bessel differential equation we solved a couple of days ago. Well, it misses the first derivative, but we did this trick a couple of days ago that we can turn this into a Bessel equation. This is exactly the differential equation we solved a couple of days ago. Just from physics. Does that make sense to you? That the biggest contribution is exactly the one that we solved a couple of days ago?
Because most of it
Of course.
looks like that.
Yeah.
Our biggest contribution is the nuclear force that had this shape. We already solved it. So naturally, if you're going to make a little perturbation, as in you change this up a little bit, then its leading part will still look like the one that we already solved. Right? This Coulomb part that we added because of the charge distribution will only mess up your solution a little bit. So the original solution still looks like this. So there we go. We know exactly how the first one looks. This we can solve. Same thing put somewhat differently. The nuclear force trumps the Coulomb force. All right. So let's look at the ones that go with epsilon. Help me out. What does that differential equation look like? Look at all the things in here that go with epsilon.
Epsilon
Same.
and r squared.
Well, it's the same derivative. But now this one with an epsilon here. What else?
E1 r squared.
Yes. There's this one?
Yeah.
Okay. Careful now, because this one is multiplied by two contributions. One of them comes with its own epsilon. In order to get only epsilon and no epsilon squares, only this one.
Yeah.
So it's U0. What else?
And
E
minus the V.
It's also E naught r squared times epsilon u1.
I agree. Do we all see this one as well? That another piece that has one epsilon in there is if you multiply this one with this part. Also gives
There's
an
an r
epsilon.
squared.
And there should be an r squared. Yes, thank you. R squared.
And minus epsilon V.
That's another epsilon v,
U0.
this one.
X R squared.
X r squared.
Times u0.
Times u0. Alright. Something else? Because we're forgetting one.
It's the constant term times epsilon u1. H bar squared at x.
Yeah.
Exactly. This part. 2m, and it's missing an epsilon now, and we're looking for epsilon parts. Let's go with u1, and that's it. There you go. All of these go with epsilon. We now have another differential equation, but now one that will give you the u1s. Note that it also consists of u0s. So this one will give you a Bessel function, and the Bessel function will become an active part of your next differential equation. Or in other words, your perturbation depends on your leading term. If you clean it up a little bit, forget about the epsilons. Those were just there to keep track of which parts to take. I'm going to divide everything into epsilons, so get rid of that part. I think this is it, yes? U1, this is 1, equals, careful now, equals this part. All the U1s I've put to the left side, and everything else goes to the right. That gives you E1 r squared U0 minus, should be minus here, is r squared U0. Alright, there's a differential equation for you, U1. Now, don't worry too much about this, because we fully know what that is. Once you've solved this differential equation, you get the Bessels back, so you know exactly what this is. You don't have to solve anything about it, you know what it is. Does this look familiar?
Shouldn't the U1 be taken out within the bracket?
Yes, thank you. That U1 I put here, yes, thank you. Does this look familiar?
This was a minus sign instead of a plus. That's it.
Yeah, there must be a minus. Yeah, okay. Yeah, maybe could have made a mistake somewhere. But anyway, it's another vessel. So all of a sudden, this very difficult problem that we had, by seeing it as, you know what, it's sort of like a main contribution and little add-ons. You find that the main contribution is just your Bessel function that you already solved. And your add-ons are also Bessel functions. So you can now solve this one, you can solve that one, add them back together at the end, and there you go. This is perturbation theory. This is how you do it. Now, don't pay too much attention to the pluses and minuses here. It's just a demonstration of how the trick works. What we're going to do next week is going to use tricks like these to actually solve differential equations like these and get numbers out. And by numbers I mean after how many seconds you expect a particle to fall out on average. Use quantum mechanics, use this little trick, use potentials like these, and we find not only that they can fly out, but we can also find typically after so many seconds we get half-lives. So in this nuclear physics course, ultimately what you have seen is not only where all these things come from, why is there alpha radiation, why is there beta radiation and such. We'll also be able to find out the actual numbers that other people have to measure. So we're really making progress here. Okay, so this is a way to solve it. Your difficult problem. Other way would have been to do it numerically.
Yeah, there was nothing that has done it this way.
Okay.
In the last like 50 years.
Okay.
But this looks much more elegant than the other ones.
Yeah, I was going to say why not? Because this looks like.
Do you not need to take the epsilon squared part?
Yeah.
Oh no, we could also do that, of course. But
Since
It's
it's
going to be a
small.
smaller.
yeah, sure. I mean, that contribution is even smaller still, but I cannot do it with what's on the blackboard right now because if somebody can see why, I cannot just take the epsilon squared parts out because they're there, right? I mean, this one and that one is epsilon squared, and I could write down the differential equation epsilon squared. But there's a reason that I'm not doing it here, and not just running out of whiteboard to write on. And that is that
We already have u1 and u0.
I only started out with things that go up to epsilon. If I want to get epsilon squared out, I would have to give the epsilon squared a fair start and add it from the outset. I did not do that. But yes, this is how you do it.
Would that be second order perturbation?
Yes, that will be that's called second order perturbation theory. This trick is ridiculously handy in all branches of physics, not just quantum mechanics and nuclear physics, it works in classical mechanics as well. And this in fact is one of the tricks that people use all the time whenever they encounter a problem that they cannot solve analytically. There's almost no problem that you can solve analytically in research physics. So it's always tricks like this that people use. You want to make it more accurate because now we've limited ourselves to around this part. You want to have a solution that also works here, add more terms.
Yeah.
And that's how you do it. How are we on time? Because that clock doesn't work.
It's 20 past 12.
Okay, so we have some time left still, yes. Okay. Feel like a break for a couple of minutes?
Yeah.
Because I would like to look at the other exercises. Okay, so thank both of you for delving into this and for presenting this.
Relaxing.
Okay, I know exactly where to cut my YouTube video on this one. So going back to the exercise we did just now, of course we did not solve it because nobody has, right? The only way that people have done it is numerically. This is how they get the magic numbers. They compare it to experiment and they find that they line up. I mean, it's it just so happens that the mathematics is too difficult and you have to do it by perturbation theory or numerically, and fortunately it goes, that works, but it's something that we cannot do here in one big exercise. Still, I do think it's worthwhile to go over this. So if I were to ask you, what is it that you pick up from doing such an exercise? It's not the magic numbers, I mean, I can imagine, but...
You need to try to split up what factors contribute in what way to your problem.
Yes.
Understanding terms.
Yes, that I mean, I was looking for something along those lines. What you really have to do is no, let me take one step back. Typically what you could do, what sometimes works, is if you have some physics, you have this formula that you apparently have to apply because some guy told you, and then you apply the formula and then you find that the mathematics doesn't work. At that moment, you're completely stuck if you don't know what the physics is behind the formula. If you have no idea what each of these terms mean, you don't know what to throw away, what you can approximate, what you can replace with something else. So the main message here is if you ever run into a physics problem that is mathematically too difficult to solve or even impossible to solve, first of all, don't worry because that happens all the time. Most of my research work consists of solving things that cannot be solved and find clever tricks to do it. That's one thing. So don't worry about that. And secondly, go back to the physics. Try to understand what each and every part of your mathematics means so you can make reasonable assumptions on how to proceed mathematically. I had this teacher once in university. He said, well, he was an experimentalist, and he said, well, you know, there's physics and there's mathematics, right? You turn your physics into mathematics and you let some computer solve the problem and then you get the answer. That's physics again. I full-heartedly disagree with that. Going through the mathematics, if the problem cannot be solved analytically, requires you to understand physics. Physics really is helping you along the mathematics, and that's really my message here. Okay, I think we did some good work this week. I think we got through the magic numbers. You know how to solve these things. You see the Schrödinger equation again. You know how to solve a central potential in principle, and you see the beginnings of a new trick to solve these things if it becomes mathematically intractable. We have a piece of tutorial left, and I would like to use that time to go through one of the exercises, maybe the one about the semi-empirical mass formula. You have to read the part in marking yourself. Not a difficult part, but you have to read it to understand how to do the exercise. I already discussed it a little bit with some of you before the tutorial started. So anyone who would like to give me a 3 or 4 sentence introduction to the semi-empirical mass formula? I hear shyness. Here's a question of conscience. Have you read?
Yes, but now I realize I was calculating and not paying attention.
Okay, no, that's good. All right. Fortunately, we're all here, so
Yeah.
here's the idea. If you have a nucleus, and you know it consists of protons and neutrons and such, more specific, Z protons and N neutrons, and together these two make up N plus Z equals A nucleons. It's the nomenclature that they use. And you go and try to predict what the mass is of this nucleus. Typically what you would do, a nice estimate of the mass, would be to just take the amount of protons multiplied by the mass of the proton, MP, and you say, well, you know what, there's also a number of neutrons in there, so it's the number of neutrons times the mass of a neutron. Again, these numbers are frighteningly equal to each other, not exactly, but almost. But sure, this is what it is, and this gives you an estimate of the mass. And then you go measure the thing, and it actually doesn't agree. And that's because of relativity. Because energy is also a form of mass. The more these things bind together, the less total mass a thing has. Binding energy is a negative number. Which is another way of saying that putting these things together tends to go to the configuration that has the least energy. That is the most stable one. That's what you get. That's exactly what we did when we filled up these nuclear shells. We were looking for that configuration where as many nucleons in the lower shells are possible, that one is the most stable. Okay, so that's what we do. So you have an estimate, but you also have the actual measurement. You get this other mass that comes out. Now the difference of these two numbers is exactly the binding energy. And it's a sizable number. So the difference of these two is the binding energy. There you go. The bigger the binding energy, the more stable the nucleus. That's what it is. I mean, relatively stable, by the way. I'm not saying that these things are actually stable in this configuration. It just means that if you have two nuclei and one of them has a big binding energy, then that thing will take longer to fall apart than the other one. It might be that it's completely stable, but it never falls apart. This is the idea. Now here's the bad thing. To calculate the binding energy on quantum mechanical grounds is extremely difficult. If there's something you can take back from the previous exercise, then it's that, how difficult it is to find these numbers, these energy values. So what people did, Woods-Saxon was the first one who did that, he devised a formula. He said, well, I expect that it sort of looks like this. That formula is a semi-empirical mass formula. It's semi-empirical because the shape of the formula sort of agrees with your theoretical prediction, but the numbers that you have to plug in to make it all fit, that has to come from an experiment. Now, I have to read this from my notebook because I always forget what the values are of each term. Here's the binding energy. Here's the formula that Woods-Saxon devised. He said the first term goes like this. Some number times A, where A is the number of protons and neutrons put together. Why? Is this something you could have read in the paragraph of Martin?
Can you repeat what you said, sorry? I didn't hear the question.
That the binding energy apparently has as one of its terms a term that is proportional to the amount of nucleons you put in there. Does that make sense?
Yeah. The more you have, the more energy.
Yeah, exactly. That's that. Yeah, that's all. But there's another term that you have to subtract, and it goes like this. It's interesting. You can understand why this is. First of all, why does it subtract?
Well, I thought of it as like a correction because like the first term is just, in general, this is what it should be, but because of a bunch of other factors, we have to subtract like big
I
corrections.
agree. Why is that from a physical point of view? You're right. The subtraction means that you have to correct for something. But apparently this is an overestimation of the energy.
Yeah.
Apparently you're taking things too big.
Yeah.
It's their rest mass.
Yeah.
Their mass, the mass you would measure of those constituent elements.
No. That's this part already.
Oh, okay.
Yeah.
So that's not a translation of that fact.
No, not at all. No. The binding energy is the difference between these two numbers.
Mm-hmm.
This part has already been taken out.
Okay.
Let me draw this for you. Here's the whole Here's the whole nucleus, right? Let's make it exactly the same picture. It's not economic what I'm doing, but you know what I mean. There you go. These two attract each other, strong nuclear force. These two as well. These two as well. All of these arrows contribute to the binding energy. They add up. That's this part. But notice that this one is pulling on that one and on that one, so this one contributes 3 times in my little scheme here. But this one contributes a lot more. Many more neighbors. The ones at the surface can only pull inwards. They have nothing outwards to pull on. So these ones in the middle that have much more directions to pull, much more neighbors to pull on, contribute much more to the binding energy, to the volume, than the ones at the surface. So in this one we assume that each and every of the nucleons pull on each and every one else. That's why it's an overestimation. Take the volume, which is a measure of how many nucleons you have in total. Assume that they all pull each other, you get this term. They don't pull all each other. The ones at the surface can only pull inward and have no neighbors outside to pull on. So you have to subtract a little bit. That's that part. The fact that it goes to 2 to the power 2 over 3. Does that make sense to you?
Just make the number smaller.
Well, that is of course true. You can also make the number smaller by just putting 8.
Yeah, that's very true.
Okay. Just a second ago, I told you that the amount of nucleons is a measure of the volume. The more volume you have, the more nucleons you could put in there. We're now talking about only nucleons at the surface. Now, if this is a volume, meter to the power 3, and you want to look at surface, then it's 2/3, because a surface goes with meter to the power 2. So if this is m to the power 3, then this is m to the power 2, it's exactly a surface. That's why it goes with that. There's that part. And the minus sign should now be obvious as well. Now then there's a Coulomb interaction, the one that we've been painstakingly trying to model. And you even longer. It also subtracts. Because it lowers the binding energy. It makes it more difficult for the strong force to put everything together if the Coulomb force is trying to push everything away. So it's another number, but we have to multiply it by how much nucleons are pushing each other away. Now for that we don't need the number 8 because there's protons and neutrons together, we only need the protons. It's only the protons that try to push each other away. So we take one proton, Z, right, this is the number of protons. How many other protons does it have to repel against?
All the other ones?
Yeah, all the other ones, so it would be Z minus 1. There you go.
Not C.
Yeah, what they typically do is say, well, we're looking at uranium or something like which has 92 protons, so you know this sort of becomes 92 squared, so it is usually approximated by Z squared. But if you look at the other ones as well, you get something like this. You have to divide it by this. Does it make sense? It should. But why not? Again, it's not a surface. It's
No, this isn't, but being divided, the top one kind of becomes like, if Z is similar to A, it's 2/3 again, it's the same.
Oh, yes, I agree with that. No, that's a good point actually, yes. But there's an easier way. What is the Coulomb interaction? This is from electrodynamics. You have 2 charges, plus and plus. What is the energy? Potential energy between them? Q, RQ.
What's something to do with this one?
Epsilon r squared?
4 pi epsilon.
R.
Not r squared, it's a force.
Oh, yeah.
The energy is derivative away from a force. It's like this. So we need a meter distance. This goes as a volume. So 1/3 of that goes as a distance. That's why it says there. See, it all makes sense. The other one, asymmetry. Now this one is interesting. Let's see if we can understand that one. 2z, that's wrong. No, that makes sense. Okay, understand. Now here's something that you might have read in Martin. You have to take it as a little factoid for now. And that is that nucleons have this tendency, nuclei have this tendency to try to have as many protons as neutrons in there. So n and z should be pretty much the same value. This is why when it binds the most. You can think about it for a while why that is. It's a quantum mechanical reason. You can put it in classical mechanical terms.
The magic number.
Sorry?
The magic number. There's the same amount of protons and neutrons.
I think that's halfway a good argument. Yeah, I mean we saw that the magic numbers are independent of whether there are protons or neutrons. So if you have a very stable configuration with 2 protons, 2 neutrons is going to be extremely stable. That was the alpha particle. They try to go to the most stable configuration, they try to go to the magic numbers, which is another way of saying that protons and neutrons tend to be the same number. And as a measure of that, you can take, well, the amount of particles together minus 2 times the number of protons. Does that make sense to you?
Yeah.
You could rewrite it maybe as 1/2 A minus Z, right? I mean, it just took 1/2 factor 2 out. If the protons and neutrons are the same number, then that means that 1/2 A will just give you the number of neutrons, yes? A is the number of protons and neutrons put together. If they are the same number, 1/2 of A is the amount of neutrons. Minus the amount of protons. The more this is close to 0, the more stable it is. That's what's written here. If it's not close to 0, the binding energy becomes less.
So it's not subtracted.
And there's a number in front and the minus sign should make sense to you. So this is a direct result of our calculation of the magic numbers. This term is there because everything tries to be as magic as possible, and better even, try to be as double magic as possible. That's the reason. You see it's a direct result of quantum mechanics or Bessel functions. Final, there's another term. Let's see if you can find the reason why that is. Sometimes it's called delta, but delta itself can have 3 values. It can be a plus value, it can be a minus value, and it can be a 0 value. And which one appears depends on your nucleus. F appears at the moment that the number of neutrons and the number of protons are even. Let me just write it down first, and then in a second let's see if we can make sense out of this. If protons and neutrons are not even, so it's uneven, odd. Excuse me, yeah, both of them are odd, exactly. Comes a negative number. Think about it for a moment. This is when one of the 2 is even and the other one is odd. Or in other words, when A is an odd number. There you go. Can someone make sense of this?
Does it have to do with their alignment of spins? So if there's an even number,
and there's the answer.
then
yes.
that they would form effective
the
bosons.
Yeah, oh, that's extremely snappy. Yeah, that is the answer. Again, they try to go to the lowest energy levels, the lowest shells. But in each shell, you can, of any type of nucleon, proton or neutron, you can put spin up and spin down. It's much easier for the 2 to have a spin up and a spin down. Yes?
Yeah.
Because then they can fit together in the same low energy state. If you want to have 2 protons with spin up, then one of them, by the Pauli exclusion principle, is forced in a higher shell. Will cost you more energy. So that's why it's there. There's that cost for you. The only thing that you need now is the values of these numbers. Now all of this is the theoretical part of the formula. But semi-empirical, these numbers, how much each term contributes, you have to get from experiment. This one, it's called the volume term, is around 17 MeV, mega electron volts. The other one It's about the same. They contribute, both of them, equally. That doesn't mean that these two cancel out, because for a different number of A, still the contribution is going to be different. The next one, the Coulomb term, is very small. It's 0.7 or so. It's 0.7. Which is another statement of that apparently Coulomb interaction is very weak compared to the nuclear force. Because all of these, all the ones except for that one, are a direct result of the nuclear shell model. Yes?
Shouldn't A sub V have units of energy per meter cube?
Which one is that? A sub V. This one?
So that it cancels out with the units of A to get electron.
You're right, there's something wrong with the units here. No, that's not true.
A is not. A is just a number.
A is just a
How
number.
much you have.
It's just a countable number.
Yeah.
It's
Like
four,
you
it's
have
15.
10. You have 10 nucleons in the thing. That's it.
When I say it's proportional to V, it's not dimensionally proportional.
I see.
Then the next one, that one, it's called the asymmetry term. It contributes at the moment that the neutrons and protons don't have the same amount. Asymmetry term, that one is actually the biggest. This one. And again, we fully understand that now by the nuclear shell model. Because the nuclear force doesn't distinguish between protons and neutrons, the shells apply to both of them, so they both want to have the same number. So there's a direct result of the nuclear force, and then there's a final one, and that really depends on the nucleus. This one is called the parity term. And depending on the nucleus, it ranges between 10 and 30 MeV, something like that. Again, now it's just a matter of getting these values from experiments. Now, when Weizsäcker devised his formula, he used his semi-quantum mechanical. He didn't know about the nuclear shell model, by the way. He only had a vague idea. It was Gubert Meyer who devised it. But Weizsäcker had a vague idea, so he got to this, let other people do these measurements, and got this out. But this is already enough to find many properties of nuclei. And this whole exercise, 2 what it was, is about finding some of these properties. We should have some time to go through a couple of them.
Yeah.
Let's pick out some fun ones. Interesting one. One of the exercises was this one. Suppose that you have this nucleus, xenon 142, right? And then the question is it stable? And if it's not stable, how does it decay? Suggestions? A couple of minutes left, we should be able to do this. By the way, I find these so important that on the lecture on Tuesday, I'm going to do this whole exercise, just with all of you. So if you haven't tried it and you haven't read it, please do so, because it is an important part of the lecture series. So don't worry too much that we're not going to finish going through this exercise. I'm going to do it again on Tuesday, but just to get a general idea. All right, so how do we do this? The question is whether it is stable, that's one, and if it decays, how?
I don't think it's stable.
What's that?
I think it's unstable
It is. How do you know?
because there's only 55 protons out of.
Oh well, that's a good argument. 55. So this term would like to have 110 total mass number. It does. There's about 30 nucleons more, 30 neutrons more, and this term becomes very important. So it becomes unstable. That's very true. Oh, but we can already answer the question then, because it wants to shed neutrons. Because it wants to get as close to the same amount of protons and neutrons as possible. So it wants to shed its 30 plus neutrons. Now, how can a nucleus get rid of a neutron?
You can beta radiation.
Which one? There's type. There's two.
Is it? Yeah. What?
Beta minus, because it creates an extra electron.
Exactly.
Mm.
It's a weak nuclear force. It turns a neutron into a proton, or in the hood, what it says, it turns a down quark into an up quark. As a result, a neutron into a proton. Charge conservation says, okay, well that cannot happen unless you also create an electron. This one is being sent out, and this thing is very happy because now it says shed a neutron, gain a proton. It's not bringing the neutrons down, by the way. It's bringing the protons up, close to each other. This amount stays the same, of course, right? The number of protons and neutrons, the total number stays the same. So you get something else out, which is 142 plus an extra protons, 56, or whatever it is, by sending out beta radiation. And now it is one step closer to nullifying this term here. So you know already from the semi-empirical mass formula that this thing, yes, is unstable, and when it decays, it does so using beta minus radiation. That's nice. Yes?
But with that argument, so for example, lead-82 has an atomic number of 210. There is a huge discrepancy between its protons and neutrons, but that's one of the most stable atoms. Like everything decays into lead in the end. So that argument seems to work in some cases, but not.
I agree with that. I agree with that. Let's think about it. That's a good question. There's a very striking counterexample to this rule. Yes, that's right. Now I have to say that the semi-empirical mass formula works for about 200 or so of the isotopes, but there are some striking ones that do not work. And it might be that lead is one of those.
Because lead is extremely stable.
No, I know it's super stable, but then again, this is not gospel. This equation, I mean, it's too quantum mechanically crude to give the right answer all of them. For one thing, it works very well for the higher ones, not so for the lower ones. Here's another question. This is one of the exercises, by the way. Here's another question. If you plot the semi-empirical mass formula, the binding energy as a function of this number, it looks something like this.
Yeah.
How do you determine what number is here? It's a mathematical question. Because this is apparently here are where the most stable isotopes are. How do you get that number?
Take the derivative with respect to a set it equal to 0.
Okay, that's how you find the maximum value of any function. So what you can do is take the binding energy, take a derivative with respect to the number of protons and neutrons, set it equal to 0, and then see what comes out. And you end up over here. This is where you find iron and such. Here's a follow-up question. What you now know is where the isotopes are with the protons and neutrons bind together, this number together being the highest number. We can ask a follow-up question, but how many protons do you need?
56.
You know the answer, but how do you get there? So again, what we have here is, if you do the math, you will find what total number of protons and neutrons are stable, or relatively stable, where the top is. But if I want to know what elements are there, I don't need A, I need Z. How do I get Z out? At the moment that I'm here, I have this number of A values that apparently are relatively stable. I want to know which actual elements are there. What are the corresponding Z numbers?
Can you differentiate it with respect to Z?
What's that?
If you differentiate it with respect to Z?
Exactly. What you do, you can also write this and put it to 0, yes? Then you find all the isotopes that have, with the number of protons that are most stable. Now, if you do this exercise, I was planning to do it in full detail, and I will do those so in a couple of days, I think, if people are interested. But if you do this, you will find that this is the answer. C1 over. This is just doing the math. A over A. This is just doing the math. Take the derivative, set it equal to 0. Okay. Now two pieces of information. If you do this one, you find the number of A values that are very stable. One of them is this 111, say. Not say, it's an actual answer. Okay, so this is in the range of 110, 111 or so. So that's all nice. There's another bump because it gives you multiple places where it's relatively stable compared to its direct environment, right? Or put in mathematical terms, it's not a global maximum, it's a local maximum. There's another one, which is around, I found 97 or so. I'm sorry, 191. Do the math, this is what comes out. What we have here is how many protons make the thing stable. It's how many protons and neutrons together. Now you can take this formula that gives you the maximum amount of protons to make things stable, plug in one of these numbers, and see which proton-neutron combination is very stable. If you plug in this one, for instance, you get 191. You put this number into that, do the calculation. What comes out is, I think it's 97. 97. Iridium. They go to our friends, the experimentalists, and ask them, how stable is this? It's indeed a stable one. So we in theory, we don't have to measure these things. You just take some derivatives, plug some numbers into each other, you get the number out. It's indeed stable. Unfortunately, because of this formula not being super exact, as your example of the lead indicates, if you plug this one in, you will find that the number of number of protons with this number of protons and neutrons put together, that makes it very stable. It's going to be silver. And that one is, I also forget which one it is, 47. Yeah. So based on our calculations, we say, oh, that one is stable. It isn't. It decays. That's not bad, by the way. I mean, I'm not looking for things that are stable, relatively stable, stable compared to the other ones. It isn't. There's isotopes of silver that are stable. Everybody who has, say, an earring or a necklace or piercing or so knows this. Okay? I mean, whereas this one decays after 6 days. So apparently, it's an okay formula. It gives you sort of the shape, but for isolated examples, it doesn't work. Your lead was a very good example. It is a very good example. Now, these, of course, fortunately, the ones that it does give the right values are much more abundant. It works in many cases. Anyway, this is what I want to say for today. So, if you haven't done the exercise with the Semi-Empirical Mass Formula, please do try it again for Tuesday. Read the corresponding paragraph. I heard that it wasn't paragraph 2.3. I thought it was in Martin's book.
It isn't. It is in the second edition.
Yeah.
Oh, okay.
But on the PDF, it's
I
not.
know. Okay, well, anyway, in any case, it's a paragraph that's called Semi-Empirical Mass Formula. It gives you a broader sense of what things mean than I just told you, and we'll go through the exercise on Tuesday. Now, that's not all. Can I take it for a second? Thank you. We are going to use perturbation theory next time. So, as a homework, I wrote here that see if you in any quantum mechanics text you can find something about the Fermi golden rule. The derivation is complicated. If you cannot follow each and every single step, that doesn't matter that much. But make sure that you understand what the rule itself says, what it tells you, what you have to put in, and why that makes sense physically. Don't worry too much about the mathematics. I am going to use that next week.